So guys, hello and welcome to Accelerator Academy. So it's a new video on one shot video on Haloalkanes and Haloarenes. So this will help you to summarize the chapter and revise it well, and we will have the drive link, like the document link in the description box, so you can take a printer of these notes and written notes. So it has been prepared by keeping in mind the interest of board students as well as JE students who want to revise the entire stuff in a nutshell. So it will be beneficial for them. So let's just go through this, and I hope that I'll be going fast through this because I hope that you have already revised the chapter once and it's for your second time or the third time revision. So I have summed it up in a 6 pages of 6 pieces. So let's just see it. Let us move on. So haloalkanes and haloarenes. Okay, this is the chapter's name: haloalkanes and haloarenes. So first comes the Finkelstein reaction. Okay, this is a name reaction, Finkelstein reaction. So Finkelstein reaction is Rx plus sodium iodide NaI in the presence of dry acetone. Remember the term, in the presence of dry acetone gives Ri plus NaX. Okay, so it's just a normal reaction. Okay, so R is any alkyl group. Any alkyl group is termed as R. So any alkyl group is termed as R. Okay, so any alkyl group R, X is a halogen atom. X is a halogen atom. Okay, X is a halogen atom. Just remember the term. I hope you know this. So Rx plus NaI. So R is a halogen atom, and R is a alkyl group. X is a halogen atom plus sodium iodide NaI in presence of dry acetone gives Ri, gives R and Ri and NaX. Okay, NaX. Okay, so let us see example. So if it's RCH2Cl, okay, so R is alkyl group and X is a halogen atom, so X here is Cl plus NaI in presence of dry acetone gives RCH2I plus NaCl. Okay, so this is an example. So NaX, X here is Cl, so NaX, so NaCl, so NaCl, and R here is RCH2, so RCH2I. Okay, this is known as Finkelstein reaction. Okay, this is known as Finkelstein reaction. This is very important name reaction. Okay, so now comes the Schwarz reaction. Okay, now comes Schwarz reaction. So Schwarz reaction is Rx. So again, R is a alkyl group and X is a halogen atom. So Rx plus AgF gives Rf plus AgBr. Okay, so yeah, in board exams you'll be asked that name the state the purpose of Schwarz reaction, or you can be asked that name the method by which only fluorohalides or the alkyl fluorides can be formed. Only fluorides can be formed. Okay, so RF is a fluoride. Okay, so this method is only used for the preparation of fluorides. Okay, note the term. This method is only used. Schwarz reaction. Schwarz reaction is only used for the preparation of fluorides. So this is the important point. Used is for the preparation of fluorides. So it is used for the preparation of fluorides. Okay, so Schwarz reaction is used in the preparation of fluorides. AgF is used. So AgF, Rx plus AgF. R is an alkyl group, X is an halogen atom. So Rx plus AgF gives Rf plus AgX. Okay, so X here is Br. Okay, so X here, I have taken an example of bromine. Okay, so you can take any other example also. So Rx plus AgF gives Rf plus AgBr. Okay, this is the thing used for the preparation of fluorides only. Schwarz reaction is used in the preparation of fluorides only. Okay, so let us move on. Now comes the Hans-Dicker reaction. Okay, Hans-Dicker reaction is very important. So in Hans-Dicker reaction, this is RC double bond to Ag. This is a silver salt of fatty acid. Okay, this is silver salt of fatty acid. Okay, this is the thing. So RC double bond to Ag plus Br2 bromine in presence of CCl4 and reflux. Okay, so CCl4 and reflux. I hope you know this reflux term. So gives RBr plus CO2 plus AgBr. Okay, so this is the thing. So Hans-Dicker reaction. In Hans-Dicker reaction, sodium silver salt of fatty acids. So silver salt of fatty acids is silver salt of fatty acid. R is alkyl group, like here also. So RC double bond to Ag plus Br2 in presence of CCl4 carbon tetrachloride or and reflux gives RBr plus CO2 plus plus AgBr. Okay, so RBr plus CO2. This is RC double bond to Ag. So CO2 comes from here. Okay, CO2 is here. CO2 comes out. So RBr plus CO2 plus AgBr. Okay, this is the thing. I hope you understand. So note one term that like if we had to prepare like RBR, okay, so this is bromide, okay, so if we had to prepare a bromide, so we can do this by Finkelstein reaction also, right? So if we put the if we put RBR, okay, so we can obtain NaBr, okay, but we can also form a bromide here also. But this method, Hans-Dicker reaction, is always used for the preparation of bromide from silver salts of fatty acids, okay. So in Hans-Dicker reaction, a silver salt of fatty acid is used plus Br2 gives, in presence of CCl4 and reflux, gives RBr, CO2 and AgBr, okay. RBr plus CO2 plus AgBr is used in the preparation of bromides, okay. Preparation of bromides, okay. Is used in the preparation of bromide. So, Hanska reaction, silver salt of fatty acid, RC double bond to Ag plus Br2, presence of CCl4 and reflux gives RBr plus CO2 plus AgBr. This is the thing. So now comes the Sandmeyer's reaction. Okay, this is very important. So like I would like to proceed like I'd like to take the two reactions at a time, Sandmeyer's and Gatterman reaction. I'm taking like all these things at a one time because both the reactions are almost similar and to the nature, almost similar in nature. So it will be easier for you to understand both the reactions in one shot. Okay. So yeah. So this is. So what is this? This is aniline. Okay. This is aniline, or this not. It's not aniline, but it's a diazonium, like it's a diazonium salt, okay, like you can term this as diazonium salt also. Like I would like to say it as a diazonium salt, like if you have gone through the video of amines, like the nitrogen containing compounds, you know that what is diazonium salts, okay. Benzene diazonium chloride, this is benzene diazonium chloride. These two compounds are benzene diazonium chloride, okay. I hope if you have I hope you know what is this, because it's a one shot video. So I hope you have learned it in your class. So this is the thing. So it is benzene diazonium chloride. In presence of Cu2, Cl2, and HCl, gives chlorobenzene and N2. Okay. In presence of Cu2, Br2, and HBr, it gives bromobenzene, N2, and a Cl minus ion. Okay. This is the thing. So this Handmaid's reaction, we use Cu2 and Cu2, Cl2 and HCl. In Gatterman reaction, we use only Cu, copper and HCl. So note the difference. In Handmaid's, we use Cu2, Cl2 and HCl. In Gatterman reaction, we use Cu and HCl. Okay, so see, we have to form chlorobenzene, right? We have to form chlorobenzene. So in order to form chlorobenzene, we need a HCl or HBr. Okay, and so here also all the reactants and the products are same, only the reagent varies, okay. Only the reagent varies. The rest of the entire things are same, the things are same. So here we use Cu and HBr, copper and HBr, and heat. So we produce bromobenzene. Here we use Cu2Br2 and HBr. So the main difference is in this. In Sandmeyer's reaction we use Cu2Br2, and in Gatterman reaction we only use copper, okay. We only use copper in present, and in Sandmeyer's reaction we use Cu2Br2. And same in case of chlorine, we use on copper and HCl, Cu and HCl we use, and in Sandmeyer's reaction we use Cu2Cl2 and HCl. Gatterman we use only copper. In Sandmeyer's reaction we use Cu2Cl2 or Cu2Br2. Okay, the end products are same, that is chlorobenzene and bromobenzene respectively. Here also chlorobenzene and bromobenzene respectively. Okay, so in the board exams you will be asked to differentiate between Sandmeyer's and Gatterman reaction. So the main difference in the Sandmeyer's and Gatterman reaction is in the reagent, where in Gatterman we use only copper, and in Sandmeyer's reaction we use Cu2Cl2 or Cu2Br2. Okay, the end products are absolutely same. Okay, so just go to this is Sandmeyer's and this is Gatterman reaction. This thing, both the things are important. Okay, important. This is very important reactions. This is the thing. Both the reactions are very important. So now comes the Bals-Schimmeln reaction. Okay, now comes the Bals-Schimmeln reaction. So this name is a bit tricky and bit difficult to remember, but don't worry, you will get to, like if you see the videos and revise constantly, you will get to like remember the term. So it's Ball-Schmidt reaction. So again, this compound, as we know, this is benzene diazonium. This is benzene diazonium chloride. So this is benzene diazonium chloride. Benzene ring is N2 plus Cl minus. Okay. So this is benzene diazonium chloride in presence of HbF4. In presence of HbF4, it gives N2 plus BF4 minus. Okay. So it is benzene diazonium tetrafluoroborate. Okay, borate. Okay, so this is the thing. If you don't need to remember, just remember the compound also, because from the compound we can derive the name. Because since it was benzene diazonium chloride, benzene this N2 N2 plus, so it's diazonium. Benzene, this is benzene ring, this is diazonium, and this is chloride. Okay, so in this same case, this is benzene. Okay, this is diazonium. N2 plus is diazonium. This is FBF4. Okay, so BF4 is tetrafluoroborate. Okay, so benzene diazonium tetrafluoroborate is formed on treatment with HbF4, and this compound on heating gives fluorobenzene plus N2 plus BF3. Okay, the BF3 is also formed. So this is the thing. So in Ball-Schmidt reaction, benzene diazonium chloride on treatment with HbF4 forms benzene diazonium tetrafluoroborate. Benzene diazonium chloride or treatment with HbF4 forms benzene diazonium tetrafluoroborate, and that benzene diazonium tetrafluoroborate on heating forms fluorobenzene plus N2 nitrogen gas, and BF3 is released. Okay, so this is Ball-Schmidt reaction. It's a very important name reaction, and you will like encounter this in your conversion, like organic compound conversion questions also. So remember the name. So N2 plus Cl minus. Okay, HbF4 on treatment with HbF4 gives benzene diazonium tetrafluoroborate. That on heating gives nitrogen gas, BF3, and fluorobenzene. Okay, this is important. Okay, now comes the Dawes process. This is very important. It's the favorite question of the board exams. So it's a very important and the famous question. Okay, so let us see this thing. So Dawes process. So Dawes process is a very important and a famous reaction. It's a favorite question of the board exam also, as I mentioned earlier. So let us see. Say this is chlorobenzene, right? This is chlorobenzene. Chlorobenzene plus 2 NaOH, aqueous NaOH. So aqueous NaOH is used. Aqueous NaOH is used. Okay. So chlorobenzene plus 2 NaOH at 623 Kelvin and 300 atm pressure. Okay. So this is important. Note the reaction conditions also, because in the board exam you write accurate things. So chlorobenzene plus 2 NaOH, that is aqueous. It gives 623 Kelvin, 620 in presence of 623 Kelvin temperature and 300 atm pressure, gives benzene with O NAD. Okay, so this gives this compound. This is a reaction intermediate. Don't need to remember this. Okay, in presence this compound on reaction dilute HCl. So this compound on reaction dilute HCl gives phenol. Okay, this is phenol. So this question you will get in the form of a conversion reaction. They will not directly ask you what is Dawes process, because everyone knows, because they have prepared for Dawes process. They will give you a question that convert chlorobenzene to phenol. They will ask you to convert chlorobenzene to phenol, and the like in the board exams, the examiners have an answer key. In that answer key, Dawes process is the most accepted method. In there are other ways also, which by which you can convert like chlorobenzene to phenol also, but this is the most appropriate and the most effective method. Okay, so this is the thing. So chlorobenzene plus 2 NaOH in aqueous KOH in presence of 623 Kelvin temperature and 300 atm pressure gives ONA. Benzene gives ONA. If this on the treatment with dilute HCl gives phenol. Okay, so this is a very important reaction. I'll just mark it here. Convert chlorobenzene to phenol. Okay, convert chlorobenzene to phenol. This question will come. Okay, to convert chlorobenzene to phenol. Okay, and if you don't want to write this reaction intermediate, you can also do it by direct process. This is chlorobenzene. This is chlorobenzene. So okay, dilute aqueous NaOH, say 60 degrees Celsius, 320 atm. Okay, so like you guys will ask that earlier I mentioned 300 Kelvin and say 626 Kelvin and 300 atm. So it has not varied much. 320 atm, it's also fine. Then dilute HCl. Okay, so you write both the steps in one arrow. Okay, so you are actually writing both instead of writing this long thing, you are writing the entire thing under two arrows, okay, like under 2 points, okay. So one first reaction is NaOH C2H3C and C20ATM. The reaction intermediate formed, it is treated with dilute HCl, it gives phenol, okay. So chlorobenzene to phenol, okay. So chlorobenzene to phenol, okay. Chlorobenzene to phenol. This is important, okay. Dow's process. This is Dow's process, and Dow's process is very, very, very important. Chlorobenzene, aqueous NaOH 360 degrees C, C20 atm, pressure, dilute HCl gives phenol, okay. You can also remember by this process also. So now comes the Woods fatigue reaction. So this is from class 11. So this is from class 11. I hope you know this thing. So Wood, this is halobenzene. This is a halobenzene. It can be chlorobenzene, iodobenzene, anything. So this is a halobenzene. So halobenzene on reaction with Na, this is sodium, okay, and it is Rx. So Rx is also, R is an alkyl group and X is a halogen atom, okay, in presence of dry ether. So note the term, many students try like confuse between Finkelstein and Woods fatigue reaction, okay. In Finkelstein we use dry acetone, and in Woods fatigue reaction we use dry ether, okay. So you use dry ether. So this is the thing. So so this is a halobenzene plus Na plus Rx gives, in presence of dry ether. Dry ether is very important, or else this reaction will not take place. Gives like benzene ring attached with the alkyl group. Benzene ring is attached with the alkyl group plus NaX, okay. This is the reaction. So what does happen is that both the halogen atoms, okay, so both the halogen atom combines, okay. So the halogen atom, this thing, this halobenzene, and halogen atom of this halogen atom, both the halogens combine and they leave the group, okay, and react with sodium, and it's like a mirrored image of each other, okay. So now comes the fatigue reaction. I hope you know, I hope you are clear with what's fatigue reaction, because you already learned in class 11. So this is the thing, it comes here, it comes 2 moles of halobenzene. So 2 moles of halobenzene, okay. So 2 moles of halobenzene, so 2 moles of halobenzene in 2 moles of ether, okay, 2 moles of sodium in presence of dry ether gives biphenyl. This is biphenyl or diphenyl, anything, plus 2 NaX, okay. So in fatigue reaction, in Woods fatigue, it was a halobenzene with a alkyl benzene, okay. So like sorry, it's a halobenzene with a haloalkyl, okay. So halobenzene with haloalkyl in presence of sodium, okay, in presence of dry ether, they combine as the mirrored images and form this thing, this alkyl benzene plus NaX, okay. This is the thing in the Woods fatigue reaction. So in only fatigue reaction, you get to know that 2 moles of halobenzene in presence of 2 moles of sodium in presence of dry ether gives biphenyl. So basically that this, there are 2 moles, okay, right. So this halogen and the other, one mole of 2 mole, that total 2 moles of halogen, right. So these 2 moles of halogen, like they remove and they form a single bond between the two benzene rings. So a single bond between two benzene rings forms diphenyl, okay. This is diphenyl or biphenyl, what you can say. So, so 2 moles of halobenzene plus 2 NS, 2 moles of sodium in presence of dry ether, gives diphenyl, and 2 NaX. Okay, it's like the two images merging together. Okay, it's like two images merging together. So here it's a, see, this index finger is a benzene ring and this thumb is a halogen. Okay, and here also this index finger is a benzene ring and this thumb is a halogen, right? The two moles are combined, okay. So the two halogen atoms are combined, okay. So here single bond is formed. See, between my two thumbs, single bond is formed and there are two benzene rings, so it forms biphenyl. This forms biphenyl, okay. So I hope you are clear with it. So let us move on, okay. So now comes SN1 reaction. This is a very basic thing of organic chemistry. You have already learned in class 11, so I'll just go through it fast, okay. So R1, R2 and R3 are alkyl groups. This is central carbon and X is a halogen atom, okay. So here this X breaks, okay. This bond breaks, so it results in the formation of positive charge on carbon and negative charge on halogen atom, okay. I hope you know the basics of chemistry. So like SN1 reaction occurs in 2 steps, okay. So out of the 2 steps, this is step 1 and this step 1 is slow, okay. This is not a fast process. So this in SN1 reaction, the first process is to break the carbon halogen bond, okay. So carbon halogen bond is broken, carbon becomes positive and halogen becomes negative. So planar carbocation is formed, okay. Planar carbocation is formed. So here is a nucleophile. I hope you know what is a nucleophile, okay. Nucleophiles are negatively charged species. So this negatively charged species nucleophile reacts with positively charged carbon and forms this two compound. Okay, form this two compound. Okay, forms this two compound. Okay, so you guys will be asking that why there are two compounds formed, why is not one compound formed? This is because there are two planes. Okay, so nucleophile can attack from the attack from up. Okay, it can also attack from below. Okay, it can attack. See, this is the plane. Okay, see, my hand is a plane, my palm is a plane. So this nucleophile can attack from above also, it can attack from down also. Okay, so it can form two compounds. So these are the two possibilities. Okay, these are the two possibilities, and this is step 2. So this is step 2 and this is fast. Okay, so in SN1 reaction it takes in two steps. This takes place in two steps. That is, step 1 is bond breaking, carbon hydrogen bond breaking, that is slow formation of planar carbocation, and second is the nucleophilic attack. Second step is the nucleophilic attack. That is step 2, and step 2 is very fast. Okay, step 2 is fast. So remember the things. If you are asked to define SN1 SN2, you need to define by this entire thing. You need to draw this thing. You need to like mention the steps and step 1, step 2, the rate of the reaction, it is slow, and what is slow and what is fast. Okay, okay, so the order of reaction. Okay, so the order of reaction is this. So this is very important. 3 degree greater than 2 degree greater than 1 degree. You will be asked it in JE. Okay, you will be asked it in JE also, because this is a very famous like a very famous question in boards as well as JE or any other competitive exams. So the rate of a reaction. Okay, so the rate of a reaction is, well, is just write a thing, rate of SN1 reaction. So in SN1 reaction, 3 degree carbocation. So here 3 degree, 2 degree, 1 degree doesn't depicts temperature. It depicts the nature of carbocation. Okay. So I hope you know what is a carbocation. So 3 degree carbocation gets the. So if you don't know what is carbocation, this is a carbocation. Okay, this is a carbocation because carbon has positive charge, and any species which has positive charge is termed as cation. Okay, so this is a carbocation, carbon cation, carbocation. Okay, I hope it is clear. So the 3 degree carbocation, like it undergoes SN1 reaction very fast. 2 degrees relatively less, and 1 degree carbocation, like it's very slow. So the rate of reaction is 3 degree carbocation greater than 2 degree carbocation greater than 1 degree carbocation. This is because, see, if there are more alkyl groups, okay, if there are more alkyl groups, so it will tend to like stabilize the positive charge. If there are more alkyl groups, it will tend to stabilize the positive charge, and more the positive charge, more the stability, and more the more the positive charge, and faster it will react with negatively charged species. Okay, that is the case. So 3 degree greater than 2 degree greater than 1 degree, 3 degree carbocation undergoes the fastest, 1 degree the slowest. 1 degree carbocation undergoes SN1 reaction. This is note. This is not for SN2. This is not for any reaction. This is only for SN1 reaction. This is only for SN1 reaction, not for any other reactions. Okay. So rate of SN1 reaction. So 3 degree carbocation greater than 2 degree carbocation greater than 1 degree carbocation. Okay. So this is the thing that I just explained you in words. Okay. Like just saying you. So if you want the things in writing, and if you want to if you want the things to be presented in your exam, board exams, so you can just copy this paragraph. Okay. Just go through this. Okay. Just move on. Now comes SN2 reaction. So now comes SN2 reaction. Okay, this is very important. In SN2 reaction, this carbon halogen bond breaks. This carbon halogen bond breaks. Carbon acquires positive, and like halogen becomes negative. Okay, delta negative. This nucleophile. This is nucleophile. Okay, nucleophile attacks on carbon. It forms nucleophile attacks on carbon. Okay, nucleophile is attacked on carbon. Okay, this is a transition state. Okay, this is a transition state. Okay, and now see this very odd kind of like this intermediate state is formed. This is a very unique type of the transition state is formed. Okay, and now this halogen is removed. This halogen, this halogen is removed. This halogen is removed, and after removing this halogen, it forms this compound. Okay, it's a normal compound that has been formed. Okay, so SN2 reaction takes place in one step. Okay, so if you are asked to differentiate between SN1 and SN2, so the first point of difference is SN1 reaction takes place in two steps, SN2 reaction takes place in one step. Okay, okay, so they involve the attack of nucleophile on the alkyl halide and formation of transition state and simultaneous release of halide ions. Okay, So it is basically that it's the entire process, this formation of transitions, this breaking of bond, attack of nucleophile, formation of transition state, removal of halogen takes place in a single step and not in multiple steps. Okay, I have like depicted here in a multiple steps just to make you understand, but it's all a single step. It's just like it's nucleophile, attack of nucleophile, and this is formed, attack of nucleophile, and this is formed. Okay, these two things are not like they, like you need not write these things, but to make the examiner clear about your idea, you have to write the things. Okay, like it will be a good impression on your examiner. So they involve the attack of nucleophile on the alkyl halide and formation of transition state and simultaneous release of ions. Okay, so and simultaneously the reaction occurs. Okay, so now comes the order of SN2 reaction. So order of SN2 reaction is the reverse of SN1 reaction. SN1 reaction was 3 degree greater than 2 degree greater than 1 degree, and it is just reverse. So it's 1 degree greater than 2 degree greater than 3 degree. Okay, this thing is very important. So note the difference. This is the second point of difference. This is the second point of difference. This is the second point of difference here. Okay. This is the second point of difference. So the order is just opposite. So 1 degree greater than 2 degree greater than 3 degree for SN2, and for SN1 it was 3 degree greater than 2 degree greater than 1 degree. So this is because the attack of nucleophile depends upon static hindrance. This is because you might be given a give reason question in board exam, that is why is this order like for SN2 reactions. So this is because in 1 degree carbocation the static hindrance is less, so it undergoes nucleophilic substitution easily. 2 degree it's a little bit more, so it has some problem, and 3 degree it has the most static hindrance, so it doesn't undergo nucleophilic substitution reactions easily. This is the thing. I hope you are clear with it. So this is the order of reaction, the opposite of SN1 reaction. Okay, and the reason for this is static hindrance. Static hindrance is the keyword. You need to remember the things. Okay, you need to remember the keyword. So let us move on. So a famous question that comes in ISC is that mechanism of Dow's process. Okay, so what was Dow's process? So in Dow's process is used to convert chlorobenzene to phenol. So in Dow's process we used to convert chlorobenzene to phenol. So here this is chlorobenzene, and you know that each carbon has hydrogen is the skeletal representation, right? So chlorobenzene, this bond breaks and this hydrogen bond comes here. Okay, so NaOH is for, in terms of aqueous NaOH 350 degrees C and 300 atm pressure, it forms benzene. This is the term that examiners look for, benzene. You need, this is a benzene. Okay, here you have triple bond, here you have triple bond. Okay, so it's just like benzene, but benzene at one side has a triple bond. Benzene at one side having a triple bond is known as a benzene. So you will be asked that like in the mechanism of Dow's process, name the intermediate that is formed, and it is then the intermediate formed is benzene. This is the main thing. So in mechanism of Dow's process, the main intermediate formed is benzene. So this benzene on treatment with hydroxide ion, so OH minus ion, gives this thing. This treatment with hydrogen like H plus or H plus ion gives this phenol. This phenol on NaOH gives ONA, sodium phenoxide. This is known as sodium phenoxide. This is known as sodium phenoxide. Sodium phenoxide on treatment dilute HCl gives phenol. Okay, so this is the thing. So that is the thing. So like so benzene intermediate is formed. So benzene intermediate is formed. This is very important. Benzene, you might be encountering the term for the first time. So benzene intermediate is formed. This benzene treatment with OH minus gives this compound. This one treatment with H plus gives phenol. This phenol on treatment with NaOH gives ONA, sodium phenoxide. This gives sodium phenoxide. This sodium phenoxide on treatment with dilute HCl gives phenol. Okay, see, till here it's the mechanism. Till here this is the mechanism, and after that it's just a normal reaction. After that it's just a normal reaction. After this thing, after after this process, it's all the same in the that you have learned in the reaction, right? So the main thing to remember here is that benzene carbocation is formed, and benzene is the main intermediate in the mechanism of Dow's process. Mechanism of Dow's process, benzene is the main intermediate that is formed. Okay, so let us move on. So mechanism of chlorobenzene to aniline. Okay, so mechanism of chlorobenzene to aniline was chlorobenzene to aniline. This is chlorobenzene. This is chlorobenzene. Okay, in presence of 2NH3, 2 moles of chlorobenzene in presence of 2NH3 and Cu2O. Cu2 is the catalyst. Cu2 is the reactant here. In 475 Kelvin and 60 atm pressure, it gives 2 moles of aniline. 2 moles of aniline. 2 moles of aniline gives Cu2Cl2 and H2. Okay, gives Cu2Cl2 and H2. So if you are asked to directly convert chlorobenzene to aniline, see, you can convert chlorobenzene to aniline in multiple ways. So you can convert chlorobenzene to phenol and then phenol to aniline. You can do that. If you have learned all the chapters of organic chemistry properly, you can, like, you can relate, right? So you can, there are multiple methods, okay. But in ISC, just I'll particularly talk about ISC because they are very strict about the rules. So chlorobenzene to aniline, okay. So if you are to directly convert, like you have to convert in, one step reaction. If you had to convert chlorobenzene to aniline in a one step reaction, then you must use this process only and nothing else. You will not be rewarded any marks other than this process, okay. So 2 moles of chlorobenzene plus 2 NH3, Cu2O is the reactant here. So Cu2O in presence of 475 Kelvin pressure and 60 atm 475 Kelvin temperature and 60 atm pressure gives 2 moles of aniline, Cu2Cl2 and HCl, okay. So chlorobenzene to aniline we have converted, okay. Just go through this once. I have nothing to say here, I have nothing to explain here because mechanism doesn't come in the exam. So just go through this. This is very important for you guys. Just seriously, this question might come in ISC any day. So like it's better to like learn it previously. So this will be important for you guys. So chlorobenzene to aniline, it's a direct method. It's a direct method for converting chlorobenzene to aniline. I guess you are done. I guess if you hadn't know this thing earlier, but just go through this, take a printout of the notes and go through this. Okay, just remember the temperature and pressure conditions also, and just know the thing also. Cu2O is used here. So chlorobenzene plus 2NH3, Cu2O, pressure and temperature conditions done, gives aniline, 2 moles of aniline plus Cu2Cl2 plus H2O. I hope you are clear, right? So let us move on. So this is the thing again, okay. So chlorobenzene to aniline. So this is the mechanism of chlorobenzene to aniline. Here also the benzene carbocation is formed, okay. So here also the benzene carbocation, the benzene intermediate is formed. So chlorobenzene, the bond breaks NH2 minus, benzene is formed, benzene intermediate is formed. This benzene intermediate on treatment with NH2 forms this on treatment with hydrogen like hydrogen ion H plus ion gives aniline plus NH2 minus, okay. This is the thing. And in both, you have to remember that in both chlorobenzene to aniline and in both chlorobenzene to phenol, okay, chlorobenzene to phenol and chlorobenzene to aniline, in both the cases in the mechanism benzene intermediate is formed. This is a very important term, note the fact, okay. So benzene intermediate is formed, okay. So reduction of benzene, okay. So if you are like given that convert chlorobenzene to benzene, okay. So there are multiple methods by which you can do it, okay. There are multiple methods, but the best suited method is this. So 2 moles of chlorobenzene, 2 moles of chlorobenzene, right? 2 moles of chlorobenzene plus 2 hydrogen, 2H. So 2 moles of chlorobenzene plus 2 hydrogen in presence of nickel, aluminum or NaOH, nickel or aluminum or NaOH, or sodium amalgam and alcohol, or sodium amalgam or alcohol gives benzene. This is benzene. So plus 2H, okay. So benzene is actually reduced here, okay. Addition of hydrogen is reduction, right? So benzene is reduced here. So this is not reduction of benzene. So if you are asked to convert chlorobenzene to benzene, this is the best suited method, and you can here use like two moles of chlorobenzene plus 2 hydrogen in presence of sodium amalgam and alcohol, or nickel, aluminum, or sodium hydroxide in presence of these two catalysts. The benzene is reduced. Okay, so the benzene is reduced. Like sorry, chlorobenzene is reduced to benzene and 2HCl. Okay, so I hope you have like you know the reactions right now, and I have covered almost the entire all the important part that comes from this chapter, and all the like the top questions that comes from this chapter. I have tried to sum up most relevant parts and the most important of the parts that is available, and I have also tried to like include some of the high order thinking questions also here, because many students will leave out this part like reduction of benzene. Many students leave out, right? Like I have from my own experience I can say that many students leave out. So many students leave out this reaction mechanism of benzene, this reaction mechanism of Dow's process. They leave out. So they leave out this direct combination of chlorobenzene to aniline. Okay, so they miss out these reactions. Okay, and in the exams they use other methods to convert, and they result in getting zero in the conversion questions. So this is the thing. So it will make you easier. It will make your job easier. So this is the thing. Huh? Okay, so many students miss out this part. So I have tried to sum up the things in a very appropriate way. So go through this. If you need any help, please contact us through our website, and we have the link in the description box also. So feel free to contact us, and happy learning. Thank you.